Hey everyone, welcome back to Design Decor Camp, where we break down the world's most complex tech systems, one simple video at a time. Today, we are diving into the brains behind one of the most powerful cloud storage platforms in the world, Google Drive. Have you ever wondered how millions of people can upload, edit, and share files instantly from anywhere in the world? Or how your files are always there, safe and available, even if your laptop crashes or your phone dies? Behind the scenes, Google Drive handles petabytes of data, serves billions of read and write requests, and still maintains high availability, consistency, and security. In this video series, we are going to design Google Drive from scratch, step by step, starting with requirements, then diving into storage architecture, file synchronization, metadata, scalability, and more. Before we jump in, drop a comment below and tell me, what's the largest file you have ever uploaded to Google Drive? I'm curious. And hey, if you are new here, don't forget to hit that like, subscribe, and notification bell. Alright, let's kick off by understanding what exactly are the core requirements of a system like Google Drive. You don't want to build a skyscraper on shaky ground, right? Now that we have introduced the beast we are going to design, let's talk about what this system actually needs to do. Think of this as our blueprint, the foundation. If we don't get this right, the whole system could crash, just like your laptop during a Zoom call. In this video, we will focus on core functionality of the systems. Upload files. First and most obvious, users need to upload files. Could be documents, photos, or even massive video files, and they expect it to happen instantly. Download files. Next, they want to download them just as fast, whether they are at home, at work, or halfway up mountain with Spotify Wi-Fi. File versioning. Ever accidentally delete something or change a file and regret it? Google Drive keeps a history of file version revisions. We need to support that too. File sharing. Users should be able to share files with friends, family, or coworkers, privately or publicly. We only or edit access, granular permissions just like Google Docs. And last, notification. And here is the big one. Users should get notification when files are edited, deleted, or shared with, otherwise, it's like sending a letter with no delivery confirmation. Quick question for you. Which feature do you think is the most important in Google Drive? Comment below, I will pin the best answer. Now, let's look under the hood, the technical expectations, and non-functional requirements. Scalability. Google Drive serves billions of users. Our system needs to scale horizontally, handling crazy traffic spikes and massive storage. Reliability. You never want to hear, oops, your file is gone. So we need to make sure files are never lost with redundancy and backups. High availability. Downtime, not acceptable. Whether you are in Tokyo or Texas, Google Drive has to be available 24/7, globally. Fast sync speed. Users expect changes to reflect instantly, even if you upload a file on your phone while your laptop is open. Real-time sync is key. Last one, efficient bandwidth usage. Uploading and syncing shouldn't eat up all your data. The system needs to be smart, using data syncing, compression, and caching where it can. So to recap, we need to build a system that's not only feature-rich, but also bulletproof, blazing fast, and designed to scale. In the next video, we will break down how Google Drive might store and retrieve files at scale. Trust me, you don't want to miss it. Now, let's look into high-level design. Before you go into high-level design, sometimes interviews prefer you to design into API. User interviews prefer you to work on API design or design a database schema. So chat with the interviewer first before you jump into high-level design. Now, let's look into high-level design. In high-level design, we will first focus on functional requirements. Our first functional requirement is users should be able to add or upload file. So in this case, the request will go through load balancer. Load balancer will send the request to web servers. And web servers will send requests to upload API. In this case, when we are trying to upload the file, it has basically two parts. It has upload metadata, like file metadata. So we will save file metadata into metadata database. and we will save the actual file into S3. It's good to use S3 because it has really good support for large objects. Now, when we are discussing about like uploading file, we need to consider that there might be files which might be large files. Some files might be 1 MB, some might be 10 MB, versus some might be 1 GB. So in this case, we need to consider that certain components might not be able to support 1 GB of file, or that might be certain limitations on components. As an example, when we are using load balancer, it has a limitation of, it has a default time of it has default time 60 seconds. So let's discuss about the limitations. We should also consider the limitations of each components. When we are trying to transfer our data out file, which might be 1 MB or 10 MB or 1 GB, there are certain limitations on the load balancer. As an example, load balancer has an idle timeout of 60 seconds. So when you're trying to upload a file which might be 1 GB, and if that file upload takes more than 60 seconds, the request will drop out and the upload will fail. In this case, we need to make sure that either we should increase the idle timer from 60 seconds to more based on our requirement. Second thing is, when we are using load balancer to transfer file, it also adds extra latency, as well as we have to pay extra for data transfer. So by considering all these issues with load balancer, I would suggest that we should transfer file directly to S3 instead of using load balancer. Another case, here we should consider that when we are trying to transfer file of 1 GB, it will be still slower to upload files of 1 GB on S3 directly. So instead of uploading 1 GB file on S3 directly, we will add block servers. Basically, we would transfer big files or small files into small chunks onto S3. So I'm adding here block servers. So our request will go from users to block servers, and block servers will send small blocks of data onto S3. And this is how our upload functionality work. This is a very high-level overview of how we should upload files onto database as well as on S3. I will also suggest to add metadata cache. By doing that, if there are any changes or anything, or if we are doing search on files, we can get results faster from metadata cache. So this is our first code functionality requirement discussion about how should we upload files. Now next, which is download files. So in download files, when users are coming on the site and they are trying to download file, the request will go through load balancer. Load balancer will send a request to web server, and web server will send a request to download API servers. Download API will request or query data into metadata cache first. If the data is available on metadata cache, then it will retrieve data from cache and then will send request back to web server and to user. This is how download API will work at high level. The next one is file revisions. For file revisions also, we will have file revisions API. The file revisions API will throw or write a query, and it will basically like fire a query on metadata cache. It will retrieve data and will return results back to users. Now, next one is share files with friends, family, or coworkers. For sharing files, when users enter request to share file to their friends or family, we will call share API. Share API will send a request to metadata database, and then it will send request to the friends to whom we are trying to send the request. Now let's discuss about share files with friends, family, or coworkers. When they try to send the request to share our data to their friends, the request will first go to share API servers, and share API will send the request to notification API, as well as it will save data into the database that this person has requested to share data with their ex-friend. And on the other side, we need to send the request to notification service, because there might be a chance that when they're trying to send a request to their friends, they might not be active. So we have to make sure that they get the notification when the user becomes active and they come online and they can see that this friend has shared some data to them. And the last one is send a notification when a file is edited, deleted or shared with you. So whenever any changes happens in terms of edit, delete or sharing the file, the request will go to notification service. Notification service will send request to message queue. Basically it will be like a backup queue. You can consider it. I would say backup queue. The reason is like whenever there are any inactive users or anything, this backup queue will have data for those inactive users. And whenever users comes online, they will get the request about any new files added, deleted or removed or any changes had happened or shared the new file with them. So this is a very high level diagram in terms of like how upload, download, share notification from functionalities will work for users. In deep dive, we will discuss about what are the non-function requirements and how do we support it in this system. So first, we will discuss about bandwidth usage. For large files that are uploaded regularly, sending the whole file on each update consumes a lot of bandwidth. Two optimizations are proposed to minimize the amount of network traffic being transmitted. First, data sync. When a file is modified, only modified blocks are synced instead of the whole file using a sync algorithm. And we should also use compression. Applying compression on blocks can significantly reduce the data size. Thus, blocks are compressed using compression algorithms depending on file types. For example, gzip and bzips2 are used to compress text files. Different compression algorithms are needed to compress images and videos. In our system, block servers do the heavy lifting work for uploading files. Block servers process files passed from clients by splitting a file into blocks, compressing each blocks, and encrypting them. Instead of uploading the whole file to the storage system, only modified blocks are transferred. So as you can see here, a file is split into smaller blocks. Each block is compressed using compression algorithm. To ensure security, each block is encrypted before it is sent to cloud storage. Now, as part of the data sync, meaning only modified blocks are transferred to cloud storage. Highlighted block 3 and block 6. Represent change blocks. Using data sync, only those two blocks are uploaded to the cloud storage. Block servers allows us to save network traffic by providing data sync and compression. So this is very like in deep dive in terms of how do we update or how do we upload files on cloud storage for bandwidth usage to save the bandwidth. Now let's discuss about our second non-functional requirement, which is fast sync speed, or you can say high consistency requirement. Our system requires strong consistency by default. It is unacceptable for a file to be shown differently by different clients at the same time. The system needs to provide strong consistency for metadata cache and database layers. Memory cache adopt an eventual consistency model by default, which means different replicas might have different data. To achieve strong consistency, we must ensure the following. Data in cache replicas and the master is consistent. Invalid cache on database write to ensure cache and database hold the same value. Now, we also need to maintain file consistency. Any modification of a file performed locally needs to be informed to other clients to reduce conflicts. Notification service is built to serve this purpose. At the high level, notification service allows data to be transferred to clients as events happens. Here are a few options, which is basically like you can use either WebSocket or you can use long pooling. Now, WebSocket basically used for bidirectional communication. Basically, like in this case, it's not really bidirectional communication. Bidirectional communication is like basically you're sending some requests and the receiver is also sending some response in the back. For example, when you're using WhatsApp or any chat system, WebSocket is really good option for those kind of system. In this case, it's only one-way communication, which is basically when you're editing or sharing anything to the user, it sends request or it sends updates to users. But we don't have to get the response back that if that user opened it or if they are doing anything. It's just one-way response. one-way request. So in this case, we will be using long polling instead of WebSocket. With long polling, each client accepts a long polls connection to the notification service. If changes to a file are detected, the client will close the long poll connection. Closing the connection means a client must connect to the metadata server to download the latest changes. After the response is received, a connection timeout is reached, a client immediately sends a new request to keep the connection open. And this is how the consistency will be maintained. Where user immediately knows there are any changes happening, they get immediate lead response. They get immediate changes related to what are the changes happened through notification service. Let's discuss about our next non-partial requirement, which is high availability. So let's consider about load balancer. Basically, high availability, you need to think about every single place, how the system is available, and if anything fails, then what will happen. So let's first look into load balancer. If a load balancer fails, the secondary would become active and pick up the traffic. Load balancers usually monitor each other using heartbeat, a periodic signal sent between load balancers. A load balancer is considered as failed if it has not sent a heartbeat for some time. So here, we will consider of having multiple load balancers. Next, block servers. So, block server failure can also happen. If a block server fails, other servers pick up unfinished or pending jobs. So here, we need to consider about multiple block servers. So just in case if it fails, there will be multiple block servers. Same case applies in terms of web servers. If any one web server fails, it will send a request to another available web server. In terms of S3, so AWS is really great option of like you can scale S3 infinitely. S3 buckets are replicated multiple times in different regions as well. If files are not available in one region, they can be fresh from different regions. The next one, API server failure. We have many different API servers based on these kind of APIs out there. So here we will consider of having multiple API servers for each type of API. If any server fails, it will immediately send a request to available server. Now, let's discuss about metadata cache. If metadata cache servers are replicated multiple times, it will be great to replicate this one. And you can replicate metadata cache in multiple ways. One is like by adding multiple nodes, and another is by sharding. So if any node fails, then it will immediately consider getting data from available node. And in terms of database, same option applies, which is like we need to consider master-slave options. If master fails, in that case, it will immediately send a request to slave server. When we'll get data from there, and it will promote one of the slave server as a master node. And in case if any slave goes down, we can always use another slave for read operations and bring another database server to replace the failed one. Now, let's look into notification service. So every online user gets a long poll connections with a notification server. Thus, each notification service is connected with many users. Even 1 million connections are opened per machine. If a server goes down, all the long poll connections are lost, so clients must reconnect to a different server. Even though one server can keep many open connections, it cannot reconnect all the lost connections at once. Reconnecting with all the lost clients is a relatively slow process. And the last one is backup queue. Queues are replicated multiple times. If one queue fails, consumers of the queue may need to resubscribe to the backup queue. So this is our third non-functional requirement, which is in terms of high availability. And the last one, which is like scalability. So here, as you can see, we actually cover scalability also here by adding multiple servers. So, for example, in future, if you're trying to scale system from 100 million users to larger system, we just add multiple servers based on where we need to scale the system, and it readily starts supporting use scale of the data. Wrap-up. In wrap-up, we can discuss about multiple options. One is there might be questions about like what else can be done in this system to improve it, and if you have any other input you would like to discuss about it. So there are a couple of things which I would like to discuss in wrap-up. One is sometimes users might think that it might be a great idea to upload fast directly to S3 instead of block servers. In this case, I select there are some drawbacks. One is, the same chunking, compression and encryption logic must be implemented on different platforms if we are removing block servers. So if we are using like iOS, Android or anything, in that case we need to figure it out. Where should we support chunking, compression and encryption algorithm? It is error prone and requires a lot of engineering effort. In our design, all those logics are implemented in a centralized place, which is block servers. Second, as a client can easily be hacked or manipulated, implementing and encrypting logic on the client side is not ideal. So that's one of the things, like when you are thinking about it, just think it in detail and see like what is the best option here. Second thing is, we can do one improvement here by adding Glacier or cold storage. So basically like there might be many inactive files which are not being used from months. So it would be better to move those inactive files into cold storage. By doing this, we will be saving a lot of cost. So this is one of the changes I also feel like. You can also discuss about like how would you do error handling. Sometimes they also ask you like what will be the best test strategy for the system, etc. That was a lot. But if you have made it this far, you now understand exactly what it takes to even begin designing something like Google Tag. Let's prevent what we have covered. Uploading download files, file version history, sharing with permissions, notifications on edits. And under the hood, real-time syncing, high availability, scalability, fast performance. Now, I want to hear your take. Which feature do you think is the hardest to build? Real-time sync, sharing the permissions, handling billions of files across the globe? Drop your answers in the comments, and I'll pin the most insightful one. And there's a bonus challenge. Can you explain data syncing in a single sentence? Try it, keep it under 15 words. Let's see who can make it the purest. If you found this helpful, give it a thumbs up and hit that subscribe button so you are always up to speed with the next system design drop. Thanks for watching. This is the start of your system design glow up. See you in the next one.